Hello, and welcome to converting polar equations to rectangular equations. The last time we had a video lesson, we talked about converting rectangular to polar. This time we're going the reverse direction. We're converting polar to rectangular. So we are still going to need these equations. They are in pink, so you don't have to copy them down, but you should have them. For the most part, we're going to be using these equations. We're going to be using all of these equations now. These are more so when we are converting polar to rectangular. So we're going to see these more frequently. I know we didn't use them last time, but I wanted them all in the same place, so we had them all. So we're going to use those equations today. Converting polar to rectangular means that we are going from, and I probably should have given more room for this, we are going from pretty much like how we did with rectangular for coordinates. We went from r comma theta to an x comma y. Those were the coordinate, but that was your transition from polar coordinates to rectangular coordinates, except now we are going from r theta in an equation to an xy in an equation. So our xy equation could look like a circle, it could look like a straight line, a linear equation is a quadratic. Probably not quadratic, but it should resemble an pretty much a rectangular coordinate that is written in x, y, or just x or just y. So let's get started. First equation, it says r is equal to 3. Right off the bat, it's not terribly helpful because we don't have anything here that we could actually substitute in. But if you notice, r squared is equal to x squared plus y squared. So ultimately, we want to convert this so that it will turn into an x and a y. And we would do that with this particular equation. That's the first one. That's r squared plus y is equal to x squared plus y squared. But right now, r is not squared. So what we have to do is we have to square both sides. You are allowed to do this. R squared just becomes r squared. 3 squared becomes 9, and then now we could substitute this in. R squared will become x squared plus y squared. 9 stays 9, and this is our equation. You could technically also write this as, so if you subtract 9 from both sides, you could write this as x squared plus y squared is equal, or minus 9 is equal to 0. So both of these are acceptable answers to this particular conversion. So now our equation is written in x, y. We are good to go. Okay. If possible, if it's not an x squared plus y squared situation, we would typically want to get y by itself, like how we do in algebra. But this one is a circle. If you remember, x squared plus y squared is equal to some number. If the coefficients for x and y are the same, it will be a circle. So let me pull up the Desmos. So just like last time, I'm going to have this on the side here. And here we have our equation. R is equal to 3. That means the radius of 3. And we can see that has a radius of 3, a circle, as we said. X squared plus y squared is equal to 9 is the exact same equation. So we see that it works. Let's go on to the next one. R is equal to 4 cosine theta. Now, this time around, we are not going to square r. It's based off the previous problem, that's probably your first logical thing to do. But we could also convert cosine theta. And this is where these new equations kick in. Cosine theta is actually equal to x over r. So we could take this part of our equation and convert this to, not writing, x over r. 4 stays the same, and leave this as r is equal to. Now, if we want to simplify, if we want to clean this up really, really quickly, we could technically call this r is equal to 4x over r, and we're good to go here. At this particular point, we want to bring the r's to the left side. So in order to get rid of this r, to bring it over, we have to multiply by r. And guess what? R's on the right cancel. R times r is the r squared that we ultimately wanted. So we get r squared is equal to 4x. R squared, just like the last problem, becomes x squared plus y squared. And since this is an x squared plus y squared, we want just everything on the same side. So we're going to bring this 4x over to the left side. We have a minus 4x, minus 4x, and we end up getting x squared minus 4x plus y squared is equal to 0. And this is our final form of the rectangular equation. So going back to Desmos, if you notice, we have r in this third equation, line 3, r4 cosine theta. It is a pretty much an ellipse that's on the far right in green. And then we add this new equation, x squared minus 4x plus y squared, and it is the exact same graph. Okay? Next one. R is equal to 5 cosecant theta. So this is actually very similar to our last example, except this time we have a cosecant. Cosecant, as we talked about, is r over y. So this one's going to be a little bit different. So we're going to still set this up the same. R is equal to 5, and we're going to convert this over r, oops, let's do this. Let's make this all one line, r over y. Since this is multiplication between the 5 and the r over y, I'm going to extend this fraction bar. So it's 5r over y. And now we're going to solve. We're going to solve for y. You're going to see what happens. Well, here, let me rephrase that. We're not going to solve for y, but it's going to end up being y. We're going to bring y to the left side. We get y times r is equal to 5r. Now, what happens here is this. If we divide both sides by r to bring them to the same side, what happens to the r's? The r's actually cancel out this time. And we actually don't have an r anymore, which is fine because we're trying to get rid of the r's anyway. We get y is equal to 5. And isn't this a linear equation? Absolutely. Y is just by itself. There's no x in this particular problem, and that's okay. So if we look at in Desmos, our fifth line here, r is equal to 5 cosecant theta, we notice that it is a horizontal line. And as we know, a horizontal line never crosses the x-axis, which is why there's no x variable in our rectangular equation. So when we graph y is equal to 5, we get the same line between the red and the blue. All right, cool. So our last one for the day is theta is equal to 4 pi over 3. Now, our three previous problems had r in them. This one has theta, which means this is pretty much just a point. Okay, it's a point in our polar coordinate, in our polar graph. 4 pi over 3 would be in quadrant 3. So it'd be down here. And that doesn't mean too much to us. But as we know, theta, and specifically tangent of theta, has a 180-degree relationship. So we would have a line that should look like this. If we know this, if we do this correctly, this should be pi over 3. Okay? And we're going to do this. We're going to show that this is going to be the line that it ultimately ends up with. Because when we're working with theta, that's the example where theta kind of just example tangent. The r's canceled out, and then we were just left with kind of theta there. So we're going to use this equation to substitute in. Or not substitute in, but we're going to use that equation to kind of build towards. So we're going to actually multiply both sides by tangent. Okay? So we're going to do tangent theta here, and then tangent of pi, or 4 pi over 3 here. Tangent of theta, we know, is y over x. And tangent of 4 pi over 3, we're going to actually need the unit circle for. So if you remember in the unit circle, we should have, let's see, this was root 3, so this is 1/2, this is 1/2 negative root 3 over 2. Oops, positive root 3 over 2. So we're going to have the negative version of that, because it's negative here. So this is going to be y over x is going to be negative root 3 over 2, all over 1/2. Okay, and those are going to be equal to each other. So So this tangent of 4 pi over 3 becomes this ratio. Okay? So we're going to have y over x is equal to, and we need to rationalize this this denominator. Let's grab blue. We are going to do some scratch work here. Negative root 3, oops, this is supposed to be negative, over 2 multiplied with negative 2 over 1. These simplify and negatives cancel out, and we end up getting just a root 3. So this becomes root 3. Oops, let's go back to red. Now, remember what I said about getting y by itself? If there's no squares, that's ideally what we want to do. So we're going to multiply both sides by x. X's cancel. We get y is equal to root 3 times x. And we're going to see that both of this equation here, or this graph here on the right, will show up in our decimals. I'm going to take these red and blue equations out. You can see 4 pi over 3 does land in this quadrant 3, right across of pi over 3 in quadrant 1. And once we do that, these two equations line up with each other. Okay? So we are now converting from polar to rectangular. The equations should still line up if you graph them on a polar graph via decimals. If you do have any questions, please let me know, and I'll happily answer them, and I'll see you in the next one. Bye.